study more and like, share, and subscribe for such more content. And comment something you want to learn.
You know, from the power plant all the way to your phone charger, our entire world is running on electricity. But here's the thing, moving all that power around isn't a perfectly efficient process. There's an energy drain happening, hiding in plain sight on every utility pole and in every substation. It's a device that's constantly, silently leaking energy. So today, let's pull back the curtain and explore this hidden world of transformer losses. Okay, get this. It's estimated that up to 3% of all the electricity generated on the entire planet is just lost as waste heat in distribution transformers. 3%. That might not sound like a lot, but it's an absolutely enormous amount of energy that's produced, paid for, but never actually used by anyone. It just vanishes, gone, before it can ever do any work for us.
So where does it all go? I mean, this isn't like a simple leak in a pipe you can just patch up. It's a fundamental consequence of physics, happening deep inside the very machines that make our electrical grid possible. To really get it, we need to look inside the box.
So these transformer losses, they really boil down to two main culprits. A good way to think about them is like two different kinds of energy tax. One is this flat tax you have to pay no matter what, just for being connected. And the other? That's more like a sales tax that goes up and up the more you use. Let's break them down.
All right, first up is what we call core loss, or sometimes iron loss. This is basically the energy it takes just to keep the transformer's core alive and magnetized. You can think of it as the rent the transformer pays 24/7 just for being plugged in, even if no one is using a single watt of electricity. And this loss is really made of two smaller parts. You've got hysteresis, which is the energy it takes to constantly flip the tiny magnetic domains in the steel core back and forth 60 times a second. And then you have eddy currents, which are like these tiny wasteful whirlpools of electricity that get stirred up inside the core itself.
The second culprit is copper loss, also known as load loss. This one is just pure heat. It's generated by the electrical resistance of the copper wires or the windings inside. You might know it from physics class as I²R loss. Now, unlike core loss, this one is completely dependent on how much electricity is flowing. The more power you demand, the higher the current and the greater the heat loss.
So here's the perfect analogy. Core loss is like a car idling at a stoplight, right? It's always burning a little bit of fuel just to stay on. But copper loss, that's like slamming your foot on the accelerator. The more power you demand, the harder you're pushing that engine, and the energy you waste as heat doesn't just go up, it absolutely skyrockets.
Okay, so we've got our two basic types of loss, the constant hum of core loss and the variable heat of copper loss. But in the real world, things get way more complicated. Operating conditions, especially how much load you put on a transformer and how hot it gets, can dramatically change the entire equation.
And this is where it gets really wild. Just look at what happens as the load on a transformer increases. You see that flat line at the bottom? That's our constant core loss, just humming along, no big deal. But look at that curving line for copper loss. It doesn't just go up, it launches skyward. This shows that doubling the work you ask a transformer to do doesn't just double the energy loss, it can actually quadruple it. That is a huge, huge penalty for pushing it too hard.
But wait, it actually gets worse. Heat creates this really nasty feedback loop. So more load means more current, which means more copper loss, which generates more heat. A hotter transformer means its copper wires actually have more electrical resistance. And more resistance means, you guessed it, even more heat from I²R loss. It's a vicious cycle that just keeps spiraling, making the transformer less and less efficient the harder and hotter it runs.
And believe me, this isn't a small effect. The data shows that for every single degree Celsius the operating temperature goes up, the load losses jump by about 0.4%. Now that might not sound like much, but just imagine a heat wave during peak summer demand. Those degrees and those wasted watts add up incredibly fast, driving up costs and straining the grid right when it's most vulnerable.
So, as if managing load and heat wasn't enough of a challenge, our modern world has thrown a brand new wrench into the works. You see, the very nature of our electricity has changed, all thanks to the demands of our digital devices. We're talking about something called harmonics, or what some people call dirty power.
So, what is it about your computer, your phone charger, or the variable speed drive in a factory that causes such a headache for the grid? Well, it's because they don't draw power in the same way an old-fashioned incandescent light bulb does. They have a totally different appetite.
All of these devices here are what we call non-linear loads. Now, unlike a simple heater that draws a nice, smooth, continuous wave of current, these modern electronics draw their power in short, abrupt pulses. Think of it like they're sipping power incredibly quickly instead of taking a long, smooth drink.
And all these abrupt little sips of power, they distort the clean, smooth wave of electricity coming from the grid. They essentially add a kind of high-frequency static, or noise, onto the power line. And transformers, which were designed for that clean, smooth 60 Hz wave, really struggle with this static. It makes them vibrate and heat up in ways they're not supposed to, which causes a huge spike in those wasteful eddy current losses we talked about earlier. To fight back against this, engineers developed a rating system called the K-factor. It's pretty simple. It's just an index of how well a transformer can handle the extra heat that gets generated by all these harmonic currents. A standard transformer, one designed for old-school linear loads, has a K-factor of 1. That's our baseline. So what does that actually mean in the real world? Well, for a building filled with computers, servers, and modern electronics, you don't just need a slightly better transformer. You might need one with a K-factor of 20. That's not a small adjustment. That is a transformer specifically built to withstand 20 times the harmonic heating effects. It's a staggering number that really shows you just how much our digital world has stressed the old grid.
Okay, let's put it all together. Achieving true efficiency isn't just about building a good transformer in a lab. It's all about understanding how it's actually going to be used out in the messy, complicated, and increasingly digital real world.
So when you really look at it, you realize that transformer efficiency isn't just one single number. It's a constantly shifting target. You have to think about how hard it's being loaded, how hot it's getting, the power factor of the load, any voltage swings, and of course all those current harmonics from our modern gadgets. All of these things create a really complex puzzle that engineers have to solve to keep waste to an absolute minimum. And here's what that puzzle looks like in real numbers. Take a standard transformer. When you switch its workload from simple linear loads to modern harmonic loads, the energy loss jumps by almost 43%. And look at this, even if you start with a more efficient low-loss model, you still get hit with that exact same 43% penalty. It just proves that being generally efficient isn't enough. You need equipment specifically designed for the kind of dirty power our world actually uses today.
And this is how we fight back against that energy drain. By understanding all these different factors, engineers can design much smarter systems. They can do things like segregate those dirty, nonlinear loads onto their own dedicated K-rated transformers. They can install equipment to improve the power factor, which lowers the overall current and cuts down on those copper losses. It's a whole strategy, a multifaceted approach to minimizing waste.
Which really leaves us with a final big question. Every single part of our lives is becoming more electrified and more digital, and that means more nonlinear loads and more new challenges for our grid. That silent, unseen energy drain we talked about, it's growing. The real challenge for the next generation of engineers isn't just about generating more power. It's about building a smarter, more resilient grid that can finally outwit the fundamental laws of loss.